Good morning. You can see the screen.
Yes, sir.
Good. So in the last lecture, we showed that for every NFA, there is an equivalent DFA, and the construction is known as the subset construction. Right? So today, let us just start with an example of the subset construction. And the particular NFA we start with has this form. So it accepts all strings of zeros and ones which end with 0, 1, right? That's the NFA. Oh yeah, this is the initial state, right? So how do we construct the equivalent DFA? Equivalent meaning they accept the same language. Well, we know that the set of states will be the power set of the set of states here So because there are 3 states here, the DFA should have 8 states. But then we don't draw those 8 states because not all of them may be reachable from the initial state. So what we do is we construct the DFA on the fly. That just means that we construct it state by state as starting from the initial state, right? So what is the initial state? If you recall, the initial state of the DFA is the set containing just Q0, right? That's the initial state. So there are only 2 letters in the alphabet. So you have to decide what the transitions are for 0 and 1. So if you look at the NFA on a 0, you can either remain in Q0 or you can go to Q1. So that means in the DFA, you'll have Q0, Q1, right? And on a 1, you just remain in Q0. Sorry. Just remain here. Clear? So for every state, there'll be two transitions. So for the initial state, that is the set containing Q0, we got the two transitions. Now let's look at this state which has Q0, Q1. So on a 0, for Q0, on a 0, you can go to either Q0 or Q1. And from Q1 on a 0, you don't go anywhere, right? So that's the empty set. Therefore, for a for the transition labeled 0, you remain in this state. Is that clear? Why that is the case? Basically, you have to consider each of these states and the set of states where you can land up in, and then take the union of all those. That's how we defined the transitions, right, of the DFA. So is this clear? What about a 1? Well, from Q0, on a 1, you remain in Q0. And from Q1, on a 1, you can go to Q2. So we have discovered a new state, a reachable state, which is Q0. Yes. And Q2. Any doubts? So we got the two transitions for the first two states, and we have discovered a new state. So what are the transitions out of this new state? On a 0, from Q0, Q2, there is only, okay, then from Q0, you can go to either Q0 or Q1. And from Q2, you don't go anywhere on a 0. So that means you go back to this state here, right? On a 0. What about a 1? Well, on a 1, from Q0, you remain in Q0. And from Q2, you don't go anywhere. So on a 1, you go back there. Yeah. And in fact, no other state is necessary because this DFA is complete. I mean, every state has two outgoing arrows, if you see. And if that is the case, no other state is reachable. Okay? So we have got everything but the set of final states. So what is the set of final states? Or what are the final states? Anyone?
Q0, Q2.
That's right. So a final state is any set of states that has a final state in the NFA N as an element. And in this particular case, this happens to be only this one, because there is only one final state in the NFA N. And Q2, that is Q2, and Q2 occurs as an element in only this particular set of states. So is this clear? So all the other states are not reachable. What are the other states? The empty set is not reachable, right? The singleton set Q1, that is not reachable. The singleton Q0, of course, is reachable. The singleton Q2 is not reachable. Q0, Q1 is reachable. Q1, Q2 is not reachable. Q1, Q2 is not reachable, and there should be one more, and that is the set of all the states. So all these 5 states are not reachable. And in fact, in this particular example, the NFA has an equal number of states. Sorry, the DFA has an equal number of states as the NFA, okay? But as we saw, there are cases where the difference can be exponential. In fact, there are examples to show that you may need all the 2 to the power n states. There are examples to show that. We saw an example where the number of states depended on the length of the string, right? So for Ln, the NFA had n plus 1 states, and the DFA had at least 2 to the power n states. Okay. Right.
Excuse me, sir.
Yes.
Sir, please discuss the case when the state having the set Q0, Q2 receives 0.
Q0, Q2.
Yes, sir.
So the transition is missing. Yeah. Sorry, this one. So from Q0 on a 0, from Q0 on a 0, you can either go to Q0 or Q1, right? And from Q2, I'm talking about the NFA n. So from Q0, you can either go to Q0 or Q1. From Q2, you don't go anywhere.
Yes, sir.
So you take the union of those 2 sets.
Yes, sir, I understood. Actually, I missed something. Okay, sir.
Right. Okay. So that's all about DFAs and NFAs and the subset construction. There is one more variant of finite automata that we want to talk about. And this is extremely convenient for many constructions. And this is finite automata with epsilon transitions. Okay, and this is important in lexical analysis, which is a phase in compilers. So it is easy to construct. These are known as Epsilon Nfa. Informally, what they can do is they can change state without reading an input symbol. That is, make an epsilon transition. So the transitions can be labeled with epsilon, right? So an example is an Epsilon Nfa that accepts decimal numbers. Okay. And decimal numbers can be of various forms. You can have something like plus 9.0 or just plus 1 dot, or there can be a minus instead of plus, and there could be just something like this, right? So all these are acceptable. Yeah. So if you want to design an Epsilon Nfa, I'll just quickly draw it. Well, you have an initial state. I'll just quickly draw it without the state labels. So this transition can be taken on epsilon plus or minus, and you can have any number of digits from 0 to 9, followed by a decimal point, followed by, sorry, I'm not labeling the states, so let me forget about that. The decimal point must be, well, it is possible that the decimal point, let me draw the automaton first. So 0 to 9 again. And any number of those. And finally, an epsilon transition. Again, this is not necessary. I'll just draw the, so this is our final state, right? So before the decimal, there could be a plus or minus sign followed by some digits, or everything could be just empty because of this epsilon, right? And after the decimal, there has to be at least one digit. And it's okay even if it's just 0, right? So that, why do we need this separate final state? Let us just see why that is the case. I need one more branch here. Yeah. So this is 0 to 9. Okay. And followed by the decimal point. And yeah. So why do I need this lower branch? Do I really need it? without the lower branch, I would accept this. Nothing before the dot, nothing after the dot. Is that possible? No, that's not possible. Is it possible? No. So anyway, this is not accepted, but this is accepted. Just 8 followed by dot. This is okay, right? This is what the lower branch allows you to do, right? In the upper branch, if you take the upper branch, then it won't allow you to accept 8 followed by dot. Okay, so that's if you don't understand this, don't worry too much. You can think of another example.
Sir, that last transition epsilon to a final state, why can't we make the that state itself the final state?
Yeah,
Why?
that was my question. If you make this the final state, would there be any difference? And I want you to think about it. Okay, just think about it. If there would be a difference, I'm not saying there would be a difference. There may or may not be. Let's just think about it. Okay, right. But you can think of another example. If right, and the language is set of strings of the form a block of A's followed by a block of B's, and then finally a block of C's. Of course, you can design a DFA or an NFA for this, but using epsilon transitions, it is quite simple. Right? You can come up with a DFA for this, but then you have to take care of the fact that the empty string of also belongs to the language, because each of these blocks could be non-empty, right? So all that is taken care of by these epsilon transitions. Anyway, so that we have seen these two examples, and that is enough. So let me just come to the formal definition. So an NFA with epsilon transitions and if an automaton contains an epsilon transition, it is inherently non-deterministic, because in this state, in this particular state, the initial state, you can either remain there, either read as an input symbol and remain there, or without even looking at the input symbol, you can go over to the next state. So that is the idea. So I mean, it is inherently non-deterministic. So an NFA with epsilon transitions is of the form writing A instead of M or N. You could have written N there. Doesn't matter. Delta. So everything is the same. Where the transition function delta is Q cross sigma union epsilon. Right arrow 2 to the Q. Right? So this is the definition, and we can extend it as usual. To delta hat. Okay, but to do that, we need to define something called the epsilon closure. The epsilon closure of a state Q is the set of states that can be reached from Q using only epsilon transition. And here's an example. Q0, this is Q1, and this is Q2. Zero, one. This is also epsilon. This is 2. Right? So this is similar to the example we saw above. So what is the epsilon closure of Q0? This is, well, the epsilon closure will always include Q0. The epsilon closure of a state will always include that state itself, plus it will include every other state that is reachable by just following epsilon transitions. So all of these will be included, right? Of course, this can be defined inductively, and it is a kind of transitive closure, and that is why it is known as Epsilon Closure, right? We are defining the epsilon closure of Q. The base case is Q itself belongs to the, I'm writing the two epsilons the same way. So maybe I should use a different epsilon, as I've done here. So if this, the inductive clause says if P belongs to the epsilon closure of Q, and there is a transition from P to R, meaning that R on an epsilon, meaning that R belongs to delta P epsilon, then R belongs to epsilon closure of Q as well, and nothing else belongs to the epsilon closure of Q other than what can be derived from using these two rules, right? So using this definition, so is the definition of epsilon closure clear? Just follow the arrows labeled epsilon starting from that state, and whatever state you can reach is in the epsilon closure, including the state itself, because on an empty string you just remain in that state, right? So this is the definition. Then we can define delta hat. The extended transition relation, sorry, transition, we're calling it a function. As follows, and this is slightly more complicated than the definition for NFAs. So the first clause says that delta hat Q epsilon is epsilon closure of Q. Okay. So it includes not just Q itself, but all the states that you can reach from Q by following these transitions labeled by epsilon. That's the basis, the base clause, and the inductive clause is, sorry, I should have written, is defined inductively. Right. So delta hat Q, well, our usual way of writing a string. So W belongs to sigma star and A belongs to sigma. So what should this be? Well, this will be the epsilon closure, the union of the sets which are epsilon closures of P, where P belongs to delta RA and R itself belongs to delta hat Q W. So to understand this inductive definition, we start from the state Q, apply the definition of delta hat inductively on the string W, which is of length less than WA, right? And that will be a set of states, right? And for all states P in that set of states, sorry, all states R belonging to that set of states that you can reach after processing or reading W, you apply delta, the transition function, right? And finally, take the epsilon closure of all those states P, followed by a union of all those. Okay. So any questions, comments, doubts about this definition? First, compute the set of states that I can reach by processing W. Then see where I can reach using that symbol A from the states I reached in the first step. And finally apply epsilon closure to all those states, and then take their union. Yeah. So if you have difficulty following this definition, you should take an example and do the computation yourself. But there are several things to note here. In general, delta hat QA is not the same as delta QA, unlike for DFAs and NFAs. In DFAs and NFAs, delta hat QA is the same as delta QA. Okay, and that is why we often drop delta hat. It is understood that it's an extension of delta, and for strings of length 1, that is a single symbol, delta hat is the same as delta for NFAs and for DFAs and NFAs. So you should confirm that. You should go back and review those definitions. But that is not the case here, right? Because delta hat involves taking an epsilon closure at the end. Okay? So it is slightly more complicated. And also, delta hat Q epsilon is in general not equal to delta Q epsilon. Okay, that you can easily see in this example. If you take in this example here, if you take Q naught, then delta Q naught epsilon is the set containing just Q1. But delta hat Q naught epsilon, sorry, that that was okay. So here, delta Q naught epsilon is just this. Sorry, Q1. Whereas delta hat Q naught epsilon will include all three states because it involves the epsilon closure. Yeah. Do you have any doubts about this?
So
Yes.
the delta of Q naught comma epsilon, won't it involve Q naught?
No. No, the way we define delta for an epsilon for an epsilon NFA is if there is a transition labeled with epsilon, right? It's as if epsilon is just another symbol, right? That's the way we define that function delta. Okay. So in some sense, the function delta treats epsilon like just another symbol. But when we come to delta hat, we take into account the fact that epsilon is not a symbol. It's the empty string. Okay. Does it answer your question?
Yes, sir.
Okay, good. So with all these definitions, we can now define the language accepted
Sir,
yes. Yes.
for the question that he asked, I have another
Yes.
doubt.
Yes.
We don't explicitly mention that on epsilon. So we can also like imagine there's an epsilon transition from Q naught back to Q naught, right? Like we can explicitly draw it because if we don't,
Yes.
yeah. So in that case, I still think that Q naught and Q1 would be there in delta of Q naught comma.
Yes. It would be there in the if that transition was there, it would be there in delta. But please understand that adding that transition will not affect the behavior of the Epsilon Nfa, right? Because when you take the Epsilon closure anyway, Q naught will be included, right? And that is, I'm just coming to that. The language accepted by an Epsilon Nfa M, did I write A for, doesn't matter what I wrote. Is the set of all strings W over the input alphabet such that delta hat Q W intersection F is non-empty. So some final state can be reached, right? And here we use delta hat as we have defined. Okay. So any questions on this? There's nothing new here. It's the same as for NFAs, except the definition of delta hat is different because it involves epsilon closure, as we just saw. And intuitively, this captures our idea of what an epsilon transition, of the meaning of an epsilon transition. Okay. Maybe you need to work on a few examples, and you'll find plenty in the book to test your understanding. But let us move on to the equivalence. Again, we can show that adding these epsilon transitions is just a matter of convenience. It doesn't give us any extra power. So these epsilon transitions, adding epsilon transitions will not allow you to accept more languages than what DFA can. So the class of languages that DFA, NFA, and NFA with epsilon transitions accept are all the same, namely the regular languages. Okay, so that's the next result. Okay, so we can, again, there are two propositions. So the first one says, given any epsilon NFA, call it E, we can find a DFAD that accepts the same language, such that LE equals LD. Okay. So this is similar to the subset construction, right? So let suitably modified with epsilon closure. So let the epsilon NFA be of this form. Then define a DFA, a deterministic finite automaton D, as follows. The set of states is just the power set of the set QE, as you would expect. But the only reachable or accessible, this word is also used, so you should be familiar with that. Accessible states are those that are epsilon closed. What do we mean by that? When a set of states is equal to its epsilon closure, we say that set of states is epsilon closed. Okay. So in this case, although the total number of the set of states is the entire power set, only some of them will be reachable from the initial state and or accessible states. And these are the ones that are epsilon closed. And the initial state Q0 D is just the epsilon closure of the initial state of the Epsilon Nfa. The set of final states is the set of all those states S, which are subsets of QE, that have a non-empty intersection with the final states of E and delta D S A. So S is a set of states of the Epsilon Nfa, and therefore it is a state in the DFA. So this is only slightly more complicated than the case for NFA. So this is the union of the epsilon closure of R, and this definition mirrors the definition of delta hat, which we just saw for epsilon NFA, right? So R, this is capital S, by the way, belonging to delta E, right? Small s A, where small s itself belongs to capital S. Okay. So this is what it means. This is a set of states, capital S, to find the transition that the new state, when you read the input symbol A, just take each element of that set, capital S, which is small s, apply the transition according to the Epsilon Nfa, and you should get a set of states, right? Take each state in that, take its Epsilon closure, and then take the union. Okay. So it is a bit more complicated than the NFA case. So the claim is the language accepted by D is the same as the language accepted by E, and the proof is we show delta hat E Q0 E W is delta hat D Q0 DW, just as we did for showing the equivalence of NFAs and DFAs for all W belonging to sigma star by induction, of course, by induction on the length of W, just as we did earlier, okay? And I'm not going to go through this proof. It is somewhat more complicated than the other one, but not much more. You just have to painfully apply all the definitions at every stage and everything will work out, okay? So it is a bit tedious and I'm not going to go through this. So let me stop there, okay? So that's the end of today's lecture.